All right, I'm Matt Van Gundy. I'm from Cisco. And so NTP is in just about everything, or rather everything that we sell relies on it in some way. And so we started to become concerned about it as we saw more vulnerabilities pop up. And so this is a very sort of truncated summary of some of the anti-patterns we came across in NTP. And I'm really excited to hear people talking about protecting legacy code because, well, the world is running on legacy code. So until we throw away everything we have and build it better, we have to figure out some way to protect what we already have. So who here is already familiar with how NTP works? OK, pretty good number of people. All right, so if you have any questions, feel free to interrupt me and stop me. But I'll try and quickly review, essentially, NTP's basic structure and security properties. So on your right, there is a server, and it has an attached reference clock. And so basically, this is like an atomic or GPS clock. It has some sort of independent and hopefully very reliable view of time. And the server's job is to provide this time to the network. And so you have some lowly client, basically says, hey, server, what time is it? The server responds with a sample from its reference clock. And this allows the client to figure out its offset and to eventually synchronize its time to the server. To deal with network delay and other problems like that, the client actually sends multiple queries, gets multiple responses, averages them together, tries to get a consistent view of the server's time. And to protect against one server that just happens to be off or misbehaving, clients are typically configured with a number of different servers. And so they're going to query each one of these servers, take a look at all of their responses, and end up selecting the best one. It's a majority voting algorithm. So in order to help form a public time infrastructure, every client, at least by default, is also a server. So the top-level servers that are connected to reference clocks directly are Stratum 1. Their clients are Stratum 2. And you can have additional lower-level clients that then use the Stratum 2 servers to basically get their time. And it forms this sort of tree structure. So some important things to note about this structure are, basically every host is both a client and a server, which means that absent other protections, your laptop will serve time to the public internet. And that means that there's a whole lot of fun stuff that you can do as an attacker. So right now, like I've just sort of described client-server mode, but NTP actually runs in a variety of other modes as well and can do so simultaneously. So there's broadcast, there's symmetric, and there's also interleaved versions of broadcast and symmetric that change, all these change the semantics of the packets and the timestamps. And so any given client can have peers in the various modes at the same time. Any questions so far? Cool. All right, so basically the way that NTP protects against off-path impersonation attacks is, say you have some off-path attacker knows that the client is communicating with the server and wants to basically forward responses from the server. NTP runs over UDP and doesn't employ any sort of source port randomization. And so what that means is that it would be trivially easy to spoof packets coming from the server, except that NTP incorporates a custom mechanism to prevent this. Have sort of a visualization of an NTP packet. And the things that I want you to take note of are these three timestamps, T1, T2, and T3. What happens is whenever the client sends out a query, it's going to put its current clock into T3 in the outgoing packet. And when the server responds, the server is actually going to take that client's T3 and put it in T1 of the response packet. And so when the client receives the server's response, basically what it'll check is, hey, is the T1 in the response packet equal to T3 in my query packet? If not, it drops it. Otherwise, it's going to accept it as a valid reply. So this essentially acts as a nonce. These timestamps include fractional seconds, and NTP also randomly permutes some of the bits of the low-order bits of the timestamp. So that means that in practice, it's about 32 bits of entropy. And so it's in the end, it ends up being relatively equivalent to TCP sequence number randomization. Ultimately, this is not too terrible of a scheme. But the way that NTP ends up being implemented is it takes all these modes and this relatively simple packet structure, and it combines all these different semantics into a single code flow that makes it incredibly hard to determine sort of what the assumptions are on the preconditions are at any point in the process. And so that's actually was the sort of genesis of a number of bugs that we found. So this is a incredibly simplified view of NTP's packet consistency checks. And yeah, I'm not kidding, like incredibly simplified. And rewritten in Python to make it a little bit easier to follow. And I kind of wanted to walk through this to sort of show how these things play out. So the first consistency check NTP applies is T3, the transmit timestamp from the server, 0? Right? This is an indication that the server is unsynchronized or has no idea what time it is, incredibly broken, at which point we should throw away the packet. So NTP marks the packet as invalid and continues on, hopefully later on throwing out the packet. Otherwise, assuming that the transmit timestamp is non-zero, it asks, well, is it equal to our origin timestamp, right? So this origin timestamp is saving the transmit timestamp seen in the last NTP packet. So this is going to prevent duplications and replays of the last NTP packet. If so, it basically marks it as invalid and immediately terminates this processing. Notice that it's only checking if it matches the last timestamp. So if it was a replay of like 2 packets later, it'll accept it, potentially. Otherwise, if we're in broadcast mode, it's basically going to skip all further tests. So okay, at this point, we're probably not in broadcast mode. If we're not in interleave mode, it applies a whole nother set of checks. It asks, all right, is the origin timestamp equal to 0? So this is the nonce that the server is supposed to be reflecting back to the client. If it is, it sets its own version of the transmit timestamp to 0, basically what it was holding on to validate the server's reply, and continues on, rather than actually checking this nonce. So it turns out that this is an artifact of symmetric mode. Because what happens is when one side goes down in symmetric mode and comes back up, it's going to send a 0 in its origin timestamp. And so in order to support that, NTP has basically bypassed its own nonce checking in its set of packet consistency checks. And so what this will allow an attacker to do is to put 0 in the origin timestamp of any packet and basically bypass that nonce check. So interestingly, if we look at the next test, we see that if the transmit timestamp it was holding on to do this nonce verification is 0, or if the origin timestamp, T1 in the packet, doesn't match that transmit timestamp, we're going to fail the nonce check and return unless this interleaving condition is true. So interestingly, this was their attempt to prevent a previous report of that 0 origin timestamp issue, but it also broke symmetric mode, and since they're in the same code path, they added this previous condition which reintroduced the bug before release. So I said, they're gonna if we fail that nonce check, we actually have another chance to get through this packet processing logic. So if the receive timestamp, which basically is marking what time we received the last packet from the server, is non-zero, and the origin timestamp is equal to that receive timestamp, this matches the semantics of interleave mode. So rather than explicitly declaring interleave mode in any form in the packets or in the configuration, NTP says, oh, we must be in interleave mode. Let's switch to interleave mode and continue on.
So this is just such a fantastic example, right? The data, your code, your data drives your code.
Yes.
Right? So if there has to be a branch, there has better be a piece of data that drives that branch. If you try to overload data, you end up with this.
Yes. Well, and so interestingly is notice that they basically were bypassing this in broadcast mode. However, that means that we could be here if we're in symmetric mode or if we're in basic client-server mode. And so we could be potentially putting a client-server association for which interleave mode is not defined into interleave mode, which in the end actually lets us change time on an NTP client.
And in fact, you have a dependence there because you set interleave to be true, and then over on the right-hand side, you check the value of interleave, right?
Over here, yes. So that comes a little bit later. And then lastly, we have our previous occurrence of this zero origin timestamp issue, where in order to prevent, basically if a query is duplicated and the server responds twice, we don't want to accept both responses from the server. So the way that they do that is after a successful nonce check, they clear that nonce. Well, unfortunately, they were clearing it to 0. So basically, if we have managed to come through and not hit either of these two failure cases, it says, okay, cool, that was a successful check. Let's set it to 0, which would mean that the next, from that point on, after a successful server reply, that nonce is 0, and an attacker can just feed, packets with a 0 origin timestamp to the client.
Again, an example of overloading data
Yes.
that saves you a byte, but makes you lose on code.
Yes, it's not tracking. Am I waiting for a response from the server? Instead, it's just like I'll clear my nonce, and that'll be good enough. Sure.
I'm sorry. Did you want to interact?
No. This is great. I just was going to take a question from the back.
Whose implementation is this that you based your Python code on?
This is the reference implementation from the NTP project.
Oh. This is the reference implementation?
Yes.
Is this in the RFC?
The actually clearing that transmit variable is in the RFC. That's a protocol level bug. Also, interleave mode has never been standardized in the RFC at all. So it's entirely an addition over and beyond the RFC.
Okay,
But yes.
So as I look at this, this is a state machine, and all your variables pretty much look binary. Packet.t1 may predict.
So the timestamps are actually 64-bit integers, but yeah.
You're not. Okay, but I mean, the only thing you're doing is an equality test on them anyway, right?
Yeah. I mean, later on they do subtractions and things, but not for the consistency checks for the most part. Yeah.
I mean, just as I look at this code,
Yeah.
right? You have a state. You basically have a controller with, and the only input that it's getting besides the binary variables is this equality check. And you've got you've got 4 or 5 actions that are sitting in the backend. So the question is, did anybody actually sit out and draw out the state machine for this thing?
No, I don't think so. And it used to be much simpler, but it has evolved over time and it's been refactored. And maybe this is a good time to say that this is, probably not so testable. The actual overall design of NTP is very monolithic, and so it means that you can't unit test most pieces of it. And so it shouldn't surprise you that there are virtually no tests, which means that every time it's had a feature added or refactored, there's essentially no validation that previous functionality still works as intended, or functionality that shouldn't have been there remains, rejected. Any other questions? Okay. Yeah, and keep in mind this is incredibly simplified. So if we're, basically at this point we're probably, if we've made it down in these if checks, we're in interleave mode. And so it basically, at this point is checking again, is the server unsynchronized? Or, here, as I mentioned, in interleave mode, it uses the receive timestamp instead of the transmit timestamp. So it says, if that's non-zero or not equal to the origin timestamp from the server, then we're going to fail the interleave mode check. At this point, finally, we ask, is the packet correctly authenticated? If not, we bail it out. If so, then if it's not interleave mode, we go ahead and update our receive timestamp and the origin timestamp so that we can prevent replays of that last packet. At this point, if we have detected an error in any one of these cases that had a setting of this flash variable that didn't return, only now after updating these timestamps do we return, exit the packet processing code. Yeah.
Let's just
Anyways.
expose all the guts of that code to
Yeah.
At the very end, you know what, we don't want to.
Yeah, so anyways, basically what I'm trying to convey overall is there's an incredible number of paths for this code. And it's not clear at many points exactly what the preconditions are or what the programmer thought the preconditions would be. And so that means that you can do things like ingress packets with a timestamp of 0 or flip a basic client-server association into interleaved mode, which is undefined, by setting the T1 in the incoming packet to the time the client last received a packet from the server. And then at that point, you can then bypass this other check and, again, set time on the client. I'm out of time. There are like 1 or 2 more things I can show you, but if you want to stop here and go to the panel, I'm fine with that.
Well, we have one more presentation.
Okay.
But how we're doing terribly well on time.
Okay.
And we're getting some of the discussion that we've taken.
Sure. So there are also, so if you notice here, an interesting decision to me is that they have this curious value of the authentication variable, crypto. This actually comes from the RFC in a sense. It says ephemeral associations are mobilized upon the arrival of a packet and are demobilized upon error or timeout. An ephemeral association means that when an NTP gets a packet from a machine that it doesn't recognize, it has the potential to set up a new association and synchronize time with that system. Luckily, by default, those packets are required to be authenticated, which means you have to share a cryptographic key with the system that is receiving that packet in order for it to actually set up that association. But we might ask at the protocol level, well, how does it know like when the remote side, so I guess not explicitly stated in this quote, is that when there's an authentication error on the remote side and I've set up an ephemeral association, I demobilize that association. Well, how do I know? The remote side sends a crypto NAC. It says, hey, I failed to authenticate your packet for some reason. Please, do whatever you need to do. So how that works is NTP authenticates its packets by forming we'll call it a MAC, over. It's got its own problems. But over this unauthenticated portion, it basically appends a key ID and adds the digest from the message authentication code. Well, it turns out that they wanted to have this crypto NAC support, so they decided, well, key ID of 0 without a digest is going to mean a cryptographic negative acknowledgement, which means that is an unauthenticated packet because it doesn't bear a digest. It's also, as you notice, handled very late in the code after all the other packet consistency checks. And rather than up front saying, oh, this is a crypto NAC, let's do whatever we're going to do, even though it's not authenticated, and throwing it out, the way that they keep track of that is they add an additional authentication state. Instead of it's not authenticated, the authentication was OK, or there was an error, they say, well, we're going to add another state of authentication, crypto. What this means is that when ephemeral association, when it's trying to decide, am I going to bring up an ephemeral association, in most of the code, it basically says, hey, if authentication is either error or crypto, go ahead and reject this packet. Don't bring up the ephemeral association. If it's none, we're going to reject this packet if authentication is required. Otherwise, we'll bring up a new association. Unfortunately, for symmetric active mode packets, they introduced some additional logic to try and maintain compatibility with some broken clients. And basically, they said, all right, well, if authentication is not enabled or error, basically, we're going to fall down into the special code for special clients. Otherwise, mobilize an association. And they forgot to cover the crypto NAC case, which means that all an attacker has to do to induce a victim to set up an association and synchronize time with it is send them one of these unauthenticated crypto NAC packets. And it'll set up this association. And so we might ask at this point, well, how does the attacker know what key in order to actually communicate over this, what should be an authenticated association? Well, it turns out that NTP also reuses key ID 0 internally to mean it's unauthenticated. So that crypto NAC packet sets up an unauthenticated association, at which point the attacker can then just use unauthenticated symmetric NTP and control the victim's clock. And the attacker can basically do this as many times as necessary in order to actually override any legitimate time sources a victim might have. So one other fun thing we found was the ability to spoof Refclocks. So internally, NTP, it has all these peers. Well, how do you keep track of them? Well, we identify them by IP address. We put them in a peer list. But we may have one or more Refclocks, so how do we keep track of those? We'll put them in our peer list. But peers are identified by IP address. Well, we'll identify Refclocks by IP address, even though they don't really have one. So where do we get these IP addresses? Well, so we identify our remote peer that we're synchronizing to using their IP address. So we'll just assign a local host IP address to our Refclock. And whenever we get a Refclock packet, we'll basically create a fake network packet, put the Refclock's IP address on it, and process it. Does anyone see a potential problem with this? Well, on most systems, they're going to, NTP assumes that local net packets are going to be filtered out. They're Martian packets, right? Well, that's not true on all systems, and for some very good reasons. And so on those systems, the attacker just basically spoofs a packet with a Refclock IP address, and NTP will say, oh great, here's a packet from my Refclock, I better update my time.
So this is quite remarkable. I think we've firmly established that overloading values and pieces of data is not just an anti-pattern. It's just this nuclear kind of an anti-pattern.
Yeah, it has the potential to get you in a lot of trouble.
So, and another thought that occurs is that inputs format is code's destiny. And if you monkey around with it like that, by overloading it, then your code's destiny is posed.
Or having certain state be implicit. It's like, well, we're in this state if this value and that value have this correspondence.
Well,
In
this
like,
case, it's a magic number, right?
Yep.
Is that going to be, you still have a problem with IPsec, right?
You mean as...
IPsec is going to take care of the spoof return address, or is it?
Well, assuming someone's using IPsec, right? Like that's not very common.
Just asking.
So IPsec could be used in order to prevent off-path spoofing. The one thing that it potentially couldn't take care of would be replays of previous legitimate packets. So I should have mentioned at the very beginning, this is not all Cisco's work. We were also collaborating with Sharon Goldberg and Anshul Malhotra at Boston University. And one of the things that they specifically found was in broadcast mode, just capture some packets, replay them to the server, and you can basically pin it at one point in time, essentially forever.